So for today, we are going to be continuing our journey into mathematics. Now, we started mathematics on Monday, and we had a brief preview of the concept of indices. On Monday, we looked at indices in terms of the laws, the applications of those laws in terms of examples, and in essence, we looked at an interesting part of indices, which is the indicial equation. As a quick recap, we talked about the concept of indices being first and foremost the usages of the laws, which include the multiplication, the division, the power multiplication, the reciprocal, which is of course the negative power law, and then the fractional law, as well as the fact that any non-zero number raised to the power of 0 gives you 1. We looked at all these laws and we put them into applications. For today, we are going to be looking into another interesting part of mathematics. Think of it as the stepbrother of indices. Wherever you can find indices, you can find this other half which we are about to talk about. And that other half is the concept of logarithms. Sometimes you can call logarithms as an additive way or a different way of writing indicial functions, right? With your indices, you can simply convert that indices into logarithms as well. Now, because of this, it means that when we begin our study into logarithms, we would also, by extension, look at the relationship between indices and logarithms, as well as how we can include and combine all those relationships into making our work easier within the two fields. Now, for logarithms, the very first thing we are going to look at is understanding what it means to write a logarithmic function. Now, when I say logarithmic functions, I'm talking about the written form of log b to base a, right? Let's take this as a general form, log b to base a. What this simply means is that I am expressing this number b in terms of this base. This is the simplest representation of logarithm you can have. So, however this number is represented is dependent on this base of operation. In this case, it is base a. A can be anything. It can be 10, which is the normal decimal base that we are familiar with. It can be 2, which is the binary base. It can be 6. It can be 1000, depending on any kind of base it might be. Whenever the base changes, the form of that number will by extension change as well. Now that we have this logarithm, how then can we link up, can we introduce this base in terms of the concept of logarithm or the concept of indices that we started with? Now, if we take m to be equal to log b to base a, of course, you can read this out in full as logarithm of b to the base of a, or log b to a in short. Now, if m is equal to log b to the base a, how then would this relate to indices? In fact, m being equal to log b to a implies that b, which is the number, is equal to a raised to the power of m. When m is equal to log b to the base of a, then b is equal to a raised to the power of m. In essence, it means that the logarithm of a number to a particular base is in fact the power of the base. The logarithm of a number with respect to a base is in fact the power of that base that equals to the number, right? The logarithm of a particular number to a base is in fact the power of that base that equals the number. Let's see examples. You know for a fact that if you say 8, I can represent 8 as 2 raised to the power 3. It therefore follows that if 8 is equal to 2 raised to the power 3, then it means that 3 is equal to the log of 8 to base 2. This you can confirm with your calculator. So on your calculator, you can simply press log 8 to the base 2 and see what you will have as your result. You will find out that log 8 to base 2 will give you 3 as a result, which is essentially telling you that 2 raised to the power of 3 will give you 8. Simple and short. Now that we have looked at how indices and logarithms can relate, let's now go forward to list out the various laws of indices. Of course, or the various laws of logarithms. So now that we have talked about the relationship between indices and logarithms, as I was saying, I said because of this relationship that exists, it means that we can easily interchange questions in indices into questions in logarithms and vice versa. If you have a question in indices that is seemingly difficult to solve, you can convert that question into its logarithmic form and use that to solve the problem. Now, before we move further, let's talk about an interesting fact. Remember that we have said in our law of indices that when we pick a raised to the power of 0 to be equal to 1, whenever a is non-zero, we can now find the logarithmic equivalent of this function. If a raised to the power 0 is equal to 1, of course, when a is non-zero, then it also follows that 0 will be equal to the logarithm of 1 to base a. That is, whenever you take the logarithm of 1 to any base, provided that base is not 0, then your result will be 1. So you can simply try that out with any source you have, your calculator, your table, as the case might be. And you find out that if you take log 1 to base, let's say 1,000, you have 0. Log 1 to, let's say, 5 million, you have 0. Log 1 to base 2, you have 0, and so on. Similarly, remember that if you take a to the power of 1, you are going to get a back as your result, right? Any value raised to the power of 1 gives that same value. Because of this, it means that 1 will obviously be the logarithm of a to the base of a. That is, whenever you have the logarithm where the number and the base are the same, then your result is immediately 1. These identities are very, very important. And by the time you begin to apply them into questions, you see exactly how important it is. Now that we have looked at it, let's now take the laws of logarithms in detail. Just as we have our laws of indices, let's see the corresponding laws of logarithms and then move forward into applying them. Now, first off, remember we have said that logarithm is simply the other side of the coin that houses indices. So if indices is the head, let's just say logarithm is the tail. Or if indices is the tail, then logarithm is the head of that same coin. So it means that where indices has its multiplication law, for logarithm, we deal with an addition law, so to speak. So whenever we have the logarithm of b plus c to the base of a, it suffices for us to write this as log b to the base of a times log c to the base of a. This is essentially, addition law. Big error. So, as I was saying, the addition law in this case, when we have log bc, to the base of a, then we can write this as log b to the base of a plus log c to the base of a. Yeah, that's more correct. So, in this case, when we have a multiplication of the number to a single base, then we can split that multiplication of the number into addition of the separate logs. Unlike the indices where you have to have a multiplication of the indices and then add the power, in this case, you have a multiplication of the number that will result into the addition of the log. For the next one, we will have log b divided by c to base a. This would give us log b to base a minus log c to base a. Simple and straightforward. This is the subtraction law, which is, of course, like the complementary version of this division law we have here. Now that we have looked at this, let's now move on to the other kinds of laws we have. Of course, just as in the indices where we can't just keep playing around with that same log, we can't just keep playing around with that same log. The same thing for these logarithms as well. We are not just limited to carrying out plus or minus or times and division as the case might be. In logarithms, we can also play around with the numbers alone. Just as we can do power multiplications here, we can also still play around with the power here as well. Now, for our third law, let's look at something very, very interesting. If you have the logarithm of b raised to the power of c to base a, then I can write this as c log b to the base of a. Essentially, what this means is that if the number you have is in fact an indices, because you would see that b raised to the power of c here is the indices that is taking the position of the number. If that's the case, then the topmost power here can be swapped to the back, and then you have the log of the base of that number to the base of the log. So log b raised to the power of c to base a gives us c log b to base a. Simple and short. Next, we will have our next rule. Now, for this case, the next rule in this case, we'll talk about the version of reciprocal that we have for laws of logarithms. Unlike, of course, you know that in indices, we have a reciprocal when we have a negative power. But in the case of logarithms, what happens or what causes us to have a reciprocal case? Now, if we have log b to base a, and for some reasons, we would like to swap the position of b and a, that is, make a the number and then make b the new base, then we can reciprocate this as 1 divided by log a to the base of b. Thus, it means that log b to base a is exactly the same thing as 1 divided by log a to base b. This is very, very important when we have to change the base of our logarithm. Let's say you have something like log 10 to base 5. Naturally, you know that, okay, to finding something in base 5 is very, very hard. But then you know that base 10 is the common log, so you can easily find something in base 10. And then you would want to write out your function in base 10. Then by the reciprocal law, I can write this as 1 divided by log 5 to base 10. And then I'm good to go. And then I can easily rewrite this as the case might be. This is one of the usefulness of the reciprocal law. Now, with that reciprocal law, we can now derive something we call the change of base for logs. Change of base in logs. Right? Of course, you notice that in this reciprocal, we are definitely changing the base, but we are using whatever is in the power to replace that old base and making that old base the new number. But in this fifth law, what we are now going to be doing is introducing a new base that suits us. Let's say you have log 5 to base 4. And then you'll be like, oh, I can't operate in base 4. It looks complicated. But then if I use the reciprocal, I will now have to operate in base 5, which is also complicated. Can I introduce a simple base for me to work on? Let's say, can I bring in base 10? How do I do that? This is what the fifth law seeks to accomplish. Now, if you have log b to base a, then I can simply write this with, let's say I want to introduce a new base m, then I can simply write this as log b to base m divided by log a to base m. This is the principle for the change of base. Log log b to base a can be written as log b to base m divided by log a to base m. At this point, what is now essential for us to work with is trying to use all these laws in examples. Now, you might be wondering that this one that we have here, how exactly is this being formed? Of course, the short form is that whatever is the original number here becomes the original number in the log of the numerator, and then whatever is the base here becomes the number in the log of the denominator. So the number here retains its number spot here, and then the base here becomes the number in the denominator, right? How did we arrive at this? We can look at that in detail as well. For now, let us keep these 5 laws in mind as we now take examples and clarifications on how to apply them. Now, I'm sure you have familiarized yourself with these laws, and at this point, what's just left is for us to apply them in laws or in examples. So, let's pick some basic examples to familiarize ourselves with the usefulness of these laws. All right, so giving ourselves a list of examples and then we solve. Of course, every single example we take here comes as references from the Jamb past question. So we are making use of the Jamb material so that it provides a very good practice platform for you for the exam. And then 3, let's evaluate log 3 to the base of 1 over 3. Okay. Let's start with this 3 and then we'll go to the others. Good. Now, for our first one, which is log 16 to base 2, how do we simplify this? Now, remember that just as we had in indices, where if you are given a big number, your goal was to simplify it into a smaller index or a smaller index. The same principle arises here as well. You have log 16 to base 2. Your first trick is, can you rewrite 16 as an indices where the base is 2? If you can write 16 as 2 raised to the power of something, then you get yourself in the right direction. The reason why we are writing 16 as 2 raised to the power of something and not, let's say, 4 raised to the power of something is because the base of operation for the logarithm is 2. So our goal is, let's express this 16 as something in terms of this base of operation, which is also 2. So I will express 16 as 2 raised to the power of something. In fact, 16 can be expressed as 2 raised to the power 4 to the base of 2. And then at this point, I can apply the law of logarithm that allows me push the uppermost power to the left side. So I have this as 4 log 2 to base 2. And then just as we said, when the base of the log and the number on the log are the same, then this logarithm will evaluate to 1. So we'll have this as 4 times 1, which means that the final result is 4. So log 16 to base 2 gives us 4 as the result. Now, for our second question, we have to evaluate that if log 2 is equal to 0.4 and log 3 is equal to 0.5, we have to evaluate log 4.5. Now, the very first thing you should have at the back of your mind is whenever you have a log form written with no base, then you have to assume that you are having that logarithm in the common log. Now, what do we call the common logarithm? The common logarithm is simply the logarithm in base 10. That is what the common logarithm is. So if we have log b, it's still the same as saying log b to base 10. So it's only the common logarithm that allows the base of the log not written. So if you see just log b, then just know that it's the same thing as log b to base 10. So it means that when we have log 2 here, we are saying log 2 to base 10, log 3 to base 10, log 4.5 to base 10. Now, let's take this question. The question says that if log 2 equals 0.4 and log 3 equals 0.5, evaluate log 4.5. So we are evaluating log 4.5. Now, the goal of this is to try as much as possible to bring in log 2 and log 3 into this function. It means if I am able to express 4.5 as a product of 2 and 3, then I'll be able to carry my work duly. Now, do not forget that 4.5 is a decimal, so I can write 4.5 as 45 over 10. And then 45 over 10, if I cut this into lowest terms, this will give me log 9 over 2. And then at this point, log 9 over 2, if I apply my law of logarithm, I can express this as log 9 minus log 2. So I have brought in log 2 into my function, but I have log 9 here. I don't have anything that relates with log 9, but then I remember that I can write 9 as log 3 raised to power 2 minus log 2. What does this mean? I have a topmost power now. I can bring it to the left. So I have this as 2 log 3 minus log 2. And then at this point, all I'm simply doing is substituting values. So 2 log 3 gives me 2 times 0.5 minus log 2, which gives me 0.4. 2 times 0.5 gives me 1, minus 0.4 will give me 0.6 as my result. Straightforward. So you'll see that the goal of this question is to make you solve these questions without having to rely on a calculator. Of course, if you were to press log 4.5 on the calculator, I'm sure you'll get your answer very, very straightforward. But then, we are asked to solve this question based on these parameters. Log 2 has to be equal to 0.4, regardless of whatever you are thinking it should be. Log 3 has to be equal to 0.5. And then, you are now to use these values to evaluate log 4.5. So you are doing this as its own or on its own without the use of a calculator. And this is very, very important, considering that Jamb, which is the CBT exam now, will only display a calculator for you on your screen, and you will not be allowed to bring in a scientific calculator or thereabout. Let's take our third. We have to evaluate log 3 to the base of 1 over 3. Now, 1 over 3 as a fraction, obviously, a proper fraction, looks very, very difficult to evaluate within that box. What if we are able to take 1 over 3 away from the base position? Like so. I can express it as 1 divided by log 1 over 3 to the base of 3. Reciprocal. And because of this, 1 over 3 is now my number. So it means I can write it as 1 divided by log 3 raised to power minus 1 to the base of 3. This is, of course, me applying the law of indices that changes the reciprocal to the power, the negative power form. And then the topmost power can come to the left. I have this as 1 divided by minus 1 log 3 to base 3. And what does this mean? You have the number and the base the same, so the log gives you 1. So it means that you have 1 divided by minus 1 as your result, which of course means that log 3 base 1 over 3 gives you minus 1. Simple and short. So you see that at this point, all we have been using to apply this question or to solve these questions are the laws of logarithms. This is how important they are. But obviously, it doesn't mean that this is the only values we can find as far as law of logarithm is concerned. Now that we have looked at these examples, let's proceed to the next bit of the session to see what else is left in logarithms. Great. Now that we have looked at these versions of logarithms, Let's now move on to take deeper examples of logarithms and introduce us into equations that use the logarithmic form.